To calculate the electric field of a single electron, you use Coulomb's law. But to map the environment of a massive random distribution of charge, Coulomb's law requires a spatial summation. You have to calculate millions of individual overlapping vectors for every single point in space, resulting in an integral that cannot actually be solved. This mathematical roadblock forces physicists to find a bypass. The solution is spatial symmetry. If we rearrange the charge into an idealized, highly symmetric shape, like an infinitely long wire, the field vectors snap into predictable alignment. We exploit this alignment using a Gaussian surface, an imaginary closed boundary projected around the charge to measure electric flux. Gauss's law relies on strict geometry. We must select a surface where the electric field is perfectly parallel or perpendicular to the boundary. When we match the right surface to the right charge distribution, complex vector calculus collapses into basic algebra. We start with our first topological test case, the infinitely long, perfectly straight charged wire. We define the charge distribution here using linear charge density, represented by the Greek letter lambda, the exact amount of charge per unit length. Because the wire extends to infinity in both directions, any upward push from a lower charge is exactly cancelled by a downward push from an upper charge. The longitudinal components eliminate each other entirely, forcing the electric field to point strictly outward along the radius. To capture this strictly radial field, the only logical Gaussian surface is a cylinder. Look at the top and bottom flat end caps of this cylinder. The radial electric field lines slide perfectly parallel along these flat planes. Because the field lines never pierce these end caps, meaning they sit at a sheer 90-degree angle to the surface's normal area vector, the flux here is exactly zero. The ends drop out of our equation entirely. Now, look at the curved sidewall. The outward pointing electric field strikes this boundary at a perfect 90-degree angle at every single point. The algebraic reduction is immediate. Total flux simply equals the constant magnitude of the electric field, E, multiplied by the surface area of the cylinder's curved wall, 2 pi r times length L. By Gauss's law, we equate this flux to the enclosed charge divided by the constant epsilon naught. The length variable neatly cancels out, isolating E to reveal our final formula, lambda over 2 pi epsilon naught r. The geometry did the heavy mathematical lifting, proving that as you move away from a one-dimensional wire, the electric field decays steadily at a rate of 1 over r. Expanding that one-dimensional wire into an infinite two-dimensional plane creates an entirely different topological environment. To account for the extra dimension, we replace linear charge density with surface charge density, denoted by the Greek letter sigma. On an infinite sheet, any sideways vector components are instantly cancelled by neighboring charges. The electric field is forced to point strictly outward, running completely parallel to the x-axis on both sides of the plane. This environment requires a new geometric tool. We enclose a section of the plane with a rectangular pillbox, positioning half of it on either side to capture a fixed area A of the surface charge. This perfectly inverts the alignment we saw with the wire. Now the electric field lines run parallel to the 4 long sidewalls of our Gaussian shape, contributing zero flux. The entire sum of the flux is forced to exit exclusively straight through the 2 flat end faces. We combine the total flux from both faces, giving us 2EA, and set it equal to the enclosed charge, sigma times area, divided by epsilon naught. When we solve for the electric field, the area variable A appears on both sides of the equation and cancels out entirely. The mathematics prove a highly counterintuitive fact. The electric field generated by an infinite plane has no distance variable. It remains rigidly constant, projecting the exact same force whether you are a millimeter or a mile away. We reach our third topology by folding that flat two-dimensional plane into a hollow, perfectly thin spherical shell. If we place an observer at a point anywhere outside this boundary, we intuitively select a larger concentric sphere for our Gaussian surface. Integrating the flux across this external boundary reliably yields the standard spherical decay rate. The field drops off cleanly at 1 over r squared. To the outside world, a uniformly charged hollow shell behaves identically to a single point charge concentrated exactly at its absolute center. But when we move past the shell and enter the hollow cavity itself, the physics radically change. We draw a new spherical Gaussian boundary entirely inside the bounds of the shell. No matter how large we make this internal sphere, the amount of charge enclosed within its boundary is exactly zero. Consequently, the total enclosed flux is also zero. The equation offers only one valid output. Inside the shell, the electric field is exactly zero at all points. The internal cavity is entirely surrounded by a massive quantity of charge, yet the geometric symmetry of the shell dictates that every inward pushing vector perfectly cancels another, creating a pristine null space within. We can synthesize all of these boundary rules to solve real macroscopic physical structures, starting with the early model of the atom. This model defines the atom as a dense positive point charge nucleus, surrounded by a uniform sphere of diffuse negative charge stretching out to a defined outer radius, r. The absolute rule governing this structure is macroscopic neutrality. The total volume of the negative electron cloud must perfectly offset the localized positive charge of the nucleus. Our final challenge is to calculate the strength of the electric field at an arbitrary distance deep inside that negative atomic cloud. This graph plots the magnitude of the electric field against radial distance. To find these internal values, we anchor a spherical Gaussian surface at the central nucleus and slowly expand it outward into the negative cloud. Unlike the hollow shell, this internal boundary encloses active charge. It traps the full power of the positive nucleus, along with a constantly growing fraction of the negative volume charge. The flux equation in this region triggers a battle of forces. The positive nucleus pushes the field outward, but as the Gaussian sphere expands, the enclosed negative volume fights back, dragging the internal field strength down. We push the Gaussian surface further until it breaches the outer edge of the atom entirely. The moment the surface exceeds radius r, a critical boundary shift occurs. The Gaussian sphere now encapsulates the entire positive nucleus and the entirety of the negative cloud. Because the total enclosed charge is now perfectly balanced, the external electric field instantly drops to zero and remains flatlined at zero as distance increases. The internal electrostatic forces are immense, but perfectly contained. The atom projects no electric field into the surrounding space, proving why solid matter is neutral. Gauss's law provides a rigorous mathematical framework proving that the spatial distribution of a charge, its sheer geometry, is exactly what dictates the physical forces we measure in the real world.